just saw the statement of the Riesz representation theorem, which tells you that positive linear functionals are actually given by integration against positive measures. So, along with it we also get a sigma algebra. So, this is going to be very similar to the Lebesgue sigma algebra and the Lebesgue measure. So, you will see regularity properties etc. As we have seen in the case of Lebesgue measure. So, we will continue with that. We will look at the space with a bit more structure. So, if you look at the statement of the Riesz representation theorem, there are two regularity statements. One is the outer regularity, which is true for all sets, but the inner regularity is true only for sets with finite measure. This is in fact can be improved if you assume a little bit more on the space X, which is what we will do now, and the Euclidean spaces and the spaces you are generally familiar with will satisfy these assumptions. Okay, so let us start. So, this is the Riesz representation theorem we had written down earlier. So, the linear functional is given by an integral, that is one, and the compact sets have finite measure, and these two are the regularity properties, right, along with completeness. So, that much we have. Okay, so, now we will look at the space with a little bit more structure or properties. So, let me define all this. So, we will have several definitions now. Definition: the space X is called sigma compact. So, sigma always denotes union, countable union. So, sigma compact will mean that X can be written as a countable. So, countable is important, union of compact sets, union of compact sets. So, you should always check that these assumptions are satisfied for Rn. Okay. So, example is Rk. So, that is one definition. Two, so a similar definition for measure spaces. So, I have X, F and mu. Now, I am not assuming anything on X is simply a space. Mu is said to be sigma finite, mu is said to be sigma finite. So, you can guess what the definition is going to be. If you can write the whole space to be union of I equal to 1 to infinity, where Ei are of course measurable sets and mu of Ei is finite. Okay, so, there is a way of writing X as union of sets with finite measure. So, again Rn with Lebesgue measure will be example, Lebesgue measure. Okay, so, Lebesgue measure is sigma finite, and you can define this for subsets. So, both the definitions make sense for subsets, right. What does it mean? So, if I look at E contained in X, E is sigma compact if E is equal to union Kj, j equal to 1 to infinity, Kj compact, right. Similarly, E contained in X, E is a measurable set, then E is sigma finite if E is union Ej, j equal to 1 to infinity with mu of Ej finite, right. So, these are natural definitions, extensions of the definition to subsets. Now, if X is locally compact T2, again the whole locally compact T2 is not necessary. We have the Borel sigma algebra of X. A measure mu on B of X is called a Borel measure. So, that is just to say it is defined on the Borel sigma algebra. It can be defined on a bigger sigma algebra than the Borel set, like we have seen in the statement of Riesz representation theorem. We have the script m which is bigger than the Borel sigma algebra. Now, regularity, mu is regular. Well, maybe let me start with the set which is regular and then we will go to mu. So, if I take E in some sigma algebra, let us say M is regular. So, you can compare it with the statement in the Riesz representation theorem, is regular if E is outer regular and inner regular. Okay, so what is outer regular? Mu of E equal to infimum of mu of V, where E is contained in V and V open. Okay. Inner regular you can approximate from inside by compact sets. So, that would be the supremum mu of K contained in E, K compact. Okay. So, this is in the context of Riesz representation theorem, and if all sets in M or in B of x, that is enough, all sets in B of x, the Borel sigma algebra are regular, then we say mu is regular. Okay. So, a regular measure is where all sets in V of x are regular. So, the Riesz representation theorem gives you outer regularity, but inner regularity is only for sets with finite measure. But this can be improved with the sigma compactness assumption. Okay. So, that is the first result we will do. So, let us state a theorem. Okay. Suppose X is locally compact T2 and sigma compact. So, that is an extra assumption. Okay. If script m and mu are given by Riesz representation theorem, so RRT. So, remember we have 5 statements there, all of them are true. Okay. So, that means we have a locally compact Hausdorff space that is a linear functional and that is given by mu. So, we have the sigma algebra M and unique positive measure mu. Okay. So, we have these two. Given by Riesz representation theorem, then we can say a little bit more. So, what are the assertions? One, if E is in M and epsilon positive, there exists a closed set F and open set V such that F is contained in E, contained in V. So, you have seen this for the Lebesgue measure and it is exactly the same statement written in one go instead of writing 2-3 statements. Mu of V minus F is less than epsilon, right. So, from the top you can approximate by open sets, from the bottom you can approximate by closed sets. This was the definition of measurability for, so you can compare it with measurability of Lebesgue measure, okay, or Lebesgue sets. Okay, that is precisely the statement here, right. B, mu is a regular. So, now you have both inner and outer regularity because the space is sigma compact. Okay. So, mu is regular Borel measure. C, well, from A you know how to deduce this. So, this actually implies, you have seen this in the case of Lebesgue measure. If I take a set in M and I can approximate it with F sigma and G delta. So, there exists a set A, F sigma, and a set B which is G delta, such that A is contained in E, contained in B, and of course, the difference between B and A is 0, right. So, this means that E is given by an F sigma set and a set of measure 0, right. This is what we did for Lebesgue measure, and that is precisely what happens here also. So, let us see the proof. Okay. So, proofs follow from whatever properties we know about the measure from the Riesz representation theorem. Okay. So, first of all, X is sigma compact. So, I can write X as K1 union K2 union K3 etc., right, or where each Kj is compact, that is just sigma compactness. Now, if I take a set E in M. Okay. So, let's see what the theorem says. The first assertion is, if I take a set E, I should be able to get a closed set F and an open set F, so that this happens. Okay. So, take E in M, then mu of E intersection K j, this is finite for every j. Why? Because mu has the property that mu of k is finite for every k which is a compact set, right. Remember, that is part of the Riesz representation theorem. So, if I intersect E with Kj, I am going to get something which is contained in Kj and Kj is compact. So, that is why. Okay. Now, because of this, there exists open set Vj containing E intersection Kj such that mu of Vj minus E intersection Kj is less than epsilon by 2 to the j. Okay. So, of course, you start with fixed epsilon positive and all that, right. We want to say that there are open sets and closed sets which will do something, right. So, well, why is this true? This is simply the definition, the regularity property. So, let's go back to the regularity property. So, you can approximate any set from outside. So, the third sorry, let us go back to the Riesz representation theorem. Yeah. So, this property that infimum of mu v is open will give me E. So, that is the outer regularity. So, this follows from outer regularity. Let us justify this. This follows from outer regularity. Why is that? So, let us do this for a set which has finite measure. So, if I take A such that mu of A is finite, then I know that mu of A is, well, by outer regularity I know this is infimum of mu v, A contained in V, V open, but these are finite ones. So, I have given epsilon, there exists Vj open such that mu Vj is less than mu of A plus epsilon by 2 to the j, right. That is true because of the infimum property, but then this tells me that if I look at mu of Vj to be equal to mu of Vj minus A, right, well, A will be contained in Vj plus mu of A, because they are disjoint, this tells me that because of mu a mu Vj minus mu a being less than epsilon 2j, this implies that mu of Vj minus a is less than epsilon by 2 to the j. Okay, so that is why this is true. Alright. So, because of this, now all that you have to do is take union, right. So, take V to be equal to union Vj. So, this we have done for Lebesgue measure. Then V minus E, well, you can prove that this is contained in because of the epsilon by 2 to the j, etc. So, I will leave this part to you because we have done this so many times now. So, then mu of V minus E is less than epsilon, right, because of epsilon by 2 to the j, and you can add them up. Now, how do you get the closed set F? So, we have the open set V now, we have to get the closed set. This is exactly the same proof, that is by apply the same thing to E complement, right. Apply the same proof to E complement. Okay. So, you will get an open set, get W open, E complement contained in W, and mu of W minus E complement is less than epsilon by 2. Okay. Well, so we have seen this W minus E complement is equal to W intersection E complement complement, which is W intersection E equal to E intersection W complement complement. So, take F to be equal to W complement, which is a closed set, because W is open, and this is simply E minus F, right. That is all we need. So, this is what we did for Lebesgue measure, and that's so this continues to be true in this abstract setting as well. So, what is the next assertion? So, let us see. B says it is a regular Borel measure, right. So, that is the next thing we have to prove. So, we know that it is outer regular, we know it is inner regular for sets with finite measure. Okay. So, what we did was A was proved. So, let us look at B. We already know regularity for, well, we know outer regularity for all sets, and inner regularity for sets with finite measure. Okay. So, now if I take some set E in M with the property that mu of E is infinity, I can write E as E intersected with Kj union j equal to 1 to infinity, right, because remember my space X is sigma compact and X is written as union Kj, right, where Kj compact. But now this have finite measure. Well, why is that? Because mu of Kj is finite, right, because mu of Kj is finite. So, then it is easy to see that mu E is supremum of such things, because so now it follows that mu E is the supremum of mu of K, where K is contained in E, K compact. Well, why is that? So, let me justify this. So, I can write E as, so write E as the limit of the increasing union. So, what do I do? So, I write E as the limit of let us say En. What is En? En is j equal to 1 to n E intersection Kj. So, all of these have finite measure, right, mu of En is finite. but En's increase to E, En's increase to E. So, mu En will increase to, mu En increases to mu E. So, I am taking mu E to be infinite. So, mu En goes to infinite, but En's have measure finite. So, mu En for each En is the supremum of mu of k, where k is contained in En now, right, and k compact by inner regularity, because that has finite measure. So, I have compact sets. So, we get compact sets k contained in the big set E such that mu of k is greater than mu of En by, let us say 2 or something like that, right, but this goes to infinity. So, the k's compact sets contained in E will have mu of k going to infinity, which is same as regularity, mu E is infinity, right. So, the supremum will become infinity. So, that's fine. So, the C part I will leave as an exercise, because this is what we did for Lebesgue measure. Once we have the statement A, then that implies C by taking appropriate unions and intersection, right. You remember, if you recall the proof, you will see that you run epsilon over 2 to the minus k or 1 by j or something like that, and you take the union or intersection of those sets, right. That is precisely what will give you this. So, A implies B, A implies C. So, just assuming that X is sigma compact, we are able to conclude that mu is a regular measure. The other two are sort of standard things, but regularity of mu is important. So, you see that it immediately, so we can conclude that the Lebesgue measure is also regular if we know that the Lebesgue measure comes from Riesz representation theorem in this setting. Okay, so we'll do that in the, so we'll construct Lebesgue measure again using Riesz representation theorem, and so we'll get all these results like regularity and so on. So, let me state one more theorem which puts an additional condition on the space. So, X is again locally compact T2 space, okay, such that every open set in X is sigma compact, So, any open set is a countable union of compact sets. Let lambda be any Borel measure, which satisfies lambda of k to be finite for every compact k. Okay. Then lambda is regular. Okay, so that is a nice thing to have. So, the extra property is that if I have every open set in X is sigma compact, then any reasonable, so remember this was our reasonable property which we wanted for measures, any reasonable measure is a regular measure. So, in particular Lebesgue measure is a regular measure if you know that every open set in Rn is sigma compact, but that is a trivial assertion. So Rn satisfies this property. Rn satisfies this property. Any open set is the union of closed cubes, and you can make them compact, right. So, we have seen that. So, proof of this uses Riesz representation theorem. So, what we do is define, so recall this is a reasonable property and that will define a linear functional, right. So, define lambda f equal to integral over x f d lambda, So, this makes sense, right. Lambda is a Borel measure, f is a continuous function, right, it is in CCX. So, it is a linear functional. So, lambda is a linear functional. Well, lambda is a positive linear functional. positive linear functional on CCX, because lambda is a positive Borel measure. So by Riesz representation theorem, now this might look a bit confusing, but I'll explain what this is. By Riesz representation theorem, there exists a sigma algebra M and mu, the measure mu, positive Borel, right, positive Borel measure mu on M, such that lambda f is given by integration against the measure mu, right. So measure mu comes from Riesz representation theorem, but we have an additional property here, X is sigma compact. Why? Because every open set is sigma compact. So X in particular is an open set, so it is sigma compact, implies mu is regular by the previous result, by the previous theorem. Okay. So we will show that. Now look at lambda f is defined by x f d lambda, right. So now we show that these measures are same. So we know that mu is regular. So we will show that lambda equal to mu, right. So we know mu is regular from Riesz representation theorem and the consequences of the Riesz representation theorem, just like what we did in the previous theorem. But the measure lambda is given to us and we prove that lambda is actually equal to mu, then since mu is regular, lambda is regular. So this is also so this is something which you should notice. So this tells me that the measure is determined by the class of functions f in CCX, right. If the integrals are same, we are saying the measures are same. So CCX is rich enough to determine the measure. Okay, that is what you should understand from this, apart from the fact that it is regular. Okay, so let's do this quickly. Let V be open, then I know that V is union Kj, j equal to 1 to infinity Kj compact, because any open set is a sigma compact set. Okay. So by Urijon's lemma, so recall Urijon's lemma, there exists, well, we have fj, these are continuous functions, and between 0 and 1, such that they are 1 on Kj, and they are 0 outside V. Right, because each Kj is contained in V. So I have this compact set contained in the open set, and I have functions like this by Urijon's lemma. Okay, so you take Gn to be maximum of the first n ones, f1, f2, etc., fn. Okay, then Gn's are increasing. Of course, you are taking maximum up to n. So Gn plus 1 is maximum up to n plus 1. So it is increasing. Well, it will increase to indicator function of V, because the Kj is union of Kj's. So this is because note that union of Kj is equal to V, that is one of the things, and Gn equal to 1 on union Kj up to n, right, because you are taking the maximum of 1 over Kj's. So you will get 1 there. So that's the reason. So by monotone convergence theorem, lambda V, lambda is a nice measure. So lambda V is the limit of integral over x Gn d lambda, right, because Gn's converge to chi V, and so by monotone convergence theorem, integral over x Gn d lambda will converge to integral over x chi V d lambda, which is lambda V. But Gn's are in CCX. So this integral, inside integral, we know is the integral of Gn with the measure d mu given by Riesz representation theorem, and by MCT this converges to mu of v. So, what we have proved is lambda v is equal to mu v for every v open. From this we have to go to all sets. Okay. So, let's do that. So, let E be a Borel set. Okay. So, then there exists V open and F closed such that F is contained in E, contained in V, and mu of V minus F is less than epsilon, right. So, given epsilon, of course, given epsilon positive, this is true. Well, what does it say? So, this tells me that mu of V is less than or equal to mu of F plus epsilon, which is less than equal to mu of E plus epsilon. So, let me write that again. We have mu of V less than or equal to mu of F plus epsilon less than or equal to mu of E plus epsilon. Okay. Now, so that is one such. Now, V minus F is open because F is closed, V is open, right. So, mu of V minus F will be equal to lambda of V minus F because they agree on open sets. So, this will be less than epsilon because mu of V minus F is less than epsilon, and so the above inequality holds, right. So, you will have lambda V less than or equal to lambda F plus epsilon less than or equal to lambda E plus epsilon. Okay. So, let us put together these two, this and this, put together, you get lambda E less than or equal to lambda V less than or equal to mu V because V is open and lambda is equal to mu on open sets less than or equal to mu E plus epsilon. So, we started with lambda E and we are ending with mu E. Okay. Similarly, mu of E I know is less than or equal to mu of V, but this is equal to lambda of V because on open sets they agree, which is less than or equal to lambda E plus epsilon. So, now if you put together these two, you see that the distance between lambda E and mu E is less than epsilon. So, this is true for every epsilon positive, implies lambda equal to mu. Okay. So, if you have equality on open sets, you can go to other sets using appropriate regularity properties. That is what we have proved. So, this is a general proof. You can think of it as a general proof. Okay, so we will stop here. What we have done so far is to state the Riesz representation theorem. We did not prove it. It is a long proof. I have referred you to the book by Rudin, Srel and complex analysis. You can see the proof there. We have looked at consequences of the Riesz representation theorem. So, one of them is that on spaces like Rn, any reasonable measure is going to be a regular measure. So, in particular the Lebesgue measure is regular. We already know that it is outer regular on all sets and inner regular on sets with finite measure, but with this now we have proved that it is actually regular on all sets. Anyway, it will be completed with the construction of the Lebesgue measure in the next few lectures. So, we will start with the construction in the next lecture.